In this video, we will cover the basics of how a convolutional neural network can be trained to identify an object in an image. Note that I assume that you have some basic knowledge about neural networks. If you like, you can have a look at my basic video about artificial neural networks. We'll first see how a basic artificial neural network can be used for image classification, and then see how to do the same thing with a convolutional neural network, CNN. Finally, I will show some basic code in Python if you like to set up your first CNN. Suppose that we have taken a picture of this digit and a picture of this digit. A picture consists of a grid of pixels. For example, this image has 4 pixels in width and 5 pixels in height. In total, the image therefore consists of 20 pixels. Each pixel has a certain value that corresponds to its brightness. The values usually span between 0 and 255. In this example, high numbers represent a black color, whereas low numbers represent a gray color, and the white background is represented by zeros. If you have a grid with numbers like this, we can create the corresponding image with a software, such as R or Python. To explain image classification in the simplest possible way, we will here only use 2 colors for our images. The corresponding numerical matrices hold normalized values, where the 1s represent the orange color, and the 0s represent the white color. We will now use a simple artificial neural network without any hidden layers to predict if these images include an even or an odd digit. The network has 20 input nodes because the images have 20 pixels, and 2 output nodes because we have 2 output classes. These are the bias weights, and these are the weights that are multiplied with the input signals to compute the values in the output nodes. This image holds the value 1 in this pixel because this pixel has a color, whereas this image holds the value 0 because the corresponding pixel in this image has no color. This input node takes the value of the pixel in the image that is located on the first row, second column, whereas this input node takes the value of the pixel in the image that is located on the 5th row, third column. In this example, I will use the logistic activation function to compute the values of the output nodes, where E is the Euler's number and Z represents the value of the bias weight, plus the sum of the products of the weights and the input nodes. The values of the weights have been optimized so that the network classifies the images as good as possible. Let's say that we would use the network to predict if this image contains an odd or an even number. We would then plug in the pixel values in the corresponding input nodes. To compute the probability that this image contains an even number, we multiply the first weight by the value of the first input node, and then we multiply the second weight by the second input node, and so forth, until we have done this for all the weights. Then we sum all these 20 products and add the bias weight. Next, we plug in the computed value in the activation function and do the math, which in this case results in a value that is approximately equal to 1. If we would compute the same thing for the odd output, the probability would be equal to approximately 0. When we have just 2 outcomes and use a sigmoid activation function, the probability of an odd number is simply equal to 1 minus the probability of an even number. This means that it would be enough to have just 1 output node for our network. Let's try to understand how the predictions are associated with the values of the weights. Note that if the weight has a large negative value, and is associated with an even number, and where the input node is equal to 1. That will reduce the value of Z, which will reduce the probability that the image contains an even number. For example, if the pixel in the 4th row, first column, is equal to 1, this will increase the probability that it is an even digit, because the associated weight is a large positive number. In comparison, the corresponding weight for an odd digit is instead a large negative number, which will reduce the probability that it is an odd digit. This makes sense, because 4 out of 5 even digits have a color in this pixel, whereas no odd digit has a color in this pixel. Since none of the images have a color in the pixel in the 2nd row, 2nd column, the associated weights to this input node are close to 0, which means that the value of this pixel will have a low impact on the prediction. Training a neural network means that we find the optimal values of the weights so that the network predicts as good as possible. To optimize the values of the weights, we let the network train on this data. For example, we plug in the values of all the pixels from this image in the input nodes and tell the network that this is an even digit. It will then change the weights so that it predicts that it is an even digit. Then we do the same for the next image and tell the network that this is an odd number, and so forth. Watch my basic video about artificial neural networks if you like to understand how the weights are optimized based on a certain loss function. Once we have trained a neural network on the images with digits, we can use it to predict if an image contains an even or an odd digit. Suppose that we would use the network to predict if this image contains an odd or an even digit. We therefore plug in the image in the corresponding pixels. To calculate the probability that this is an even digit, we plug in the bias weight here, the weight associated with the pixel on the 1st row, 1st column here, and the corresponding value of this pixel. Then we plug in the weight and the input value of the 2nd node. Then for the 3rd node, and so forth. If we sum all these terms and plug in this sum in the activation function and do the math, we will get the value that is approximately equal to 0. If we instead calculate the corresponding output value for an odd number, we see that the value is approximately equal to 1. Since the output value for an odd digit is greater than the one for an even digit, the network will predict that the corresponding image contains an odd digit. We'll now have a look at convolutional neural networks, which are special networks that have been developed to improve image recognition. To illustrate how a CNN works, we will use the following 10 images where each image represents a digit and has 25 pixels. We will here try to predict which digit that is included in the image. To explain the basics of a CNN, let's have a closer look at the image that represents a 0. In CNN, one uses a so-called filter, also called a kernel. In this example, the filter is a 2x2 matrix with some numbers. The numbers used in this filter have been optimized during the training process. The following numbers are therefore optimal for this simple example. The filter is then placed on top of the image where we perform a dot product, which means that we multiply the values in the overlapping elements, like this. Then we sum the products and add the value to a so-called feature map. Next, we slide the filter one step to the right. How far we move the filter is referred to as the stride length. Since we here move the filter 1 pixel to the right, the stride length is equal to 1. Then we do the same calculations again and continue until we have moved the filter over the entire image. This procedure is called convolution, which is used to detect local features in the image. Then we apply some activation functions on the feature map, such as the ReLU function or the sigmoid function. For simplicity, I will here use the ReLU function. The ReLU function takes a value and returns the maximum value between 0 and the value we plug in. Suppose that we plug in this value here. The maximum value of these two values is simply 1, which means that we do not change this value in the feature map. The ReLU function basically sets all negative values to 0 and leaves positive values unchanged. So, for any positive input value, the output of the ReLU function is the same as the input value. Since we only have positive values in our feature map, the ReLU function does not change any of the values. Next, we may perform pooling. In this example, we use a 2x2 window and use max pooling, which means that we take the maximum value of the 4 numbers in this window and place this number here. Then we move the window to these 4 elements in the feature map and place the corresponding maximum number in the pooled feature map. Since we now move the pooling window 2 steps to the right, the stride length is here equal to 2. Per default, the stride length is usually set to the size of the pooling window. Then we move the pooling window 2 steps down, and then 2 steps to the right. Finally, we flatten the pooled feature map into a one-dimensional array, like this. Let's put our final array here. Now, suppose that we would have the following image that represents a 1. After performing convolution of the image, that would result in the following feature map and the following pooled feature map. Let's place the pooled feature map of the second image here. This is the pooled feature map of the image that contains a 0. And this is the pooled feature map of the image that contains a 1. If we would compute the same thing for the other 8 images, we will have the following data. Next, we create a fully connected network. To simplify the illustrations and calculations, I have not included any hidden layers in this network. Since our pooled feature maps have 4 values for each image, the network will have only 4 input nodes. In comparison, using a simple artificial neural network directly on the image would require 25 input nodes, 1 for each pixel. This is one important advantage of CNNs, because they will reduce the number of weights that will be optimized and focus on the important features in the image. Since we like to predict 10 different digits, the network will, in this example, have 10 output nodes. Remember that this is the bias. For example, these are the optimal values of the weights to predict if the image contains a 0. Let's see if the first image is correctly classified as a 0. We plug in the corresponding values from the pooled feature map in the input nodes and do the same calculations that we did in our previous example. Let's place the output value here. Then we compute the output value that the image contains a 1, and for the 8 other digits. We can then use the argmax function to classify the image, which means that the network predicts that the image includes a 0, because the output node for this category has the largest value. Note that these values do not sum up to 1, which means that they cannot be interpreted as probabilities. If we instead use the softmax function, the output values will instead represent probabilities, which should sum up to 1. We can now see that the network predicts that the image includes a 0 with approximately 100% probability. Remember that we use the following filter to produce the following feature map. It is, however, common to use several filters when we work with CNNs. Suppose that we would also use a second filter. Using this second filter will result in the following feature map and the following pooled feature map. We will then train a fully connected network with 8 input nodes instead of just 4. If you read more about CNNs, you will probably see these kinds of illustrations, which means that we start with one image, which corresponds to one matrix, or 3 matrices if we instead use a color image. During the convolution, we usually reduce the size of the matrix, and if we use several filters, we will get more matrices. We can also apply the filter on the feature map so that we perform several rounds of convolutions. You might wonder what numbers you should use in your filters. Well, you don't need to worry about that, because just like the weights in a fully connected network, the filters have weights that will be optimized during the training process. The weights are initialized with some random numbers, and during each round of training iteration, the weights are updated to improve the predictions. So, in total, we here have 8 weights for the 2 filters, and 80 weights that are associated with the edges between the 8 input nodes and the 10 output nodes, as well as 10 bias weights, which gives the network in total 98 weights to tune on during the training process. We will now have a look at how the network deals with color images. A color image is represented by 3 layers, or grids, which usually represent the brightness of red, green, and blue colors. The combination of the numbers in the 3 pixels then gives a certain color. In CNN, we say that we have 3 channels, one for red, green, and blue. Suppose that we would use the following filter, that we apply on all 3 channels and do the same calculations as we did before. Then we sum the calculations from the 3 channels and plug in the sum in the feature map. Next, we move the filter one step to the right, and so forth. Note that one can also include a bias weight in this calculation, so that the network has one additional way to tune on. So far, I have just shown how the calculations are done with the filters. But how do the filters identify local features in the image? Well, suppose that we would apply the following filter on the 10 images, and that it results in the 3, which we will plug in the feature map. That would mean that the filter has identified the following corner, which is present in the following images. By using also this filter, we can identify this kind of corner, which is present in the following images. So, this image is the only image that includes 2 of these corners, whereas this image is the only image that includes 2 top left corners and 1 bottom right corner. These 2 images do not include any of these corners. The image classification will therefore rely on different local features that are identified in the image, and not on individual pixels. If we would shift the digit in this image one step to the right, that would not affect the classification of this image, because the identified local features are still the same. In contrast, a simple artificial neural network would be highly affected by such a shift, because its classification is based on the exact location of the pixel values. By using a range of different filters, we can identify a large variety of local features in the images. This is one reason why we use several filters instead of just one, because different filters will learn to identify different features. We'll now discuss the meaning of padding. Remember that when we applied the filter to the image, we got the following feature map, which is a 4x4 matrix, whereas our original image is a 5x5 matrix. If we apply many convolutional steps, the feature map will become smaller and smaller and might therefore be too small to be useful. Another problem is that the pixels in the edges will have less influence when we build the feature map. For example, the pixel in the top left corner is only used once, whereas this pixel is included 4 times when the feature map is created. One way to solve these problems is to use padding, which means that we add one or several additional columns and rows to the image. The values in these extra elements are usually set to 0. If we now apply the filter to perform convolution, we see that the pixel in the top left corner will now be involved 4 times to create the feature map. We also see that the feature map will now be bigger than the original image because the feature map is now a 6x6 matrix. We can use the following formula to calculate the output size of the feature map. In our example, the size of the image is 5, and we added one padding layer around the image and used a 2x2 filter with a stride length that was equal to 1. In order to get the same size of the feature map as the image, we can simply use a larger filter, so that the feature map becomes a 5x5 matrix. We'll now have a look at some Python code if you like to reproduce some of the results shown in this video. I will also show some code based on the classical MNIST dataset. We will first set up a code for a convolutional neural network to classify the same images that were used in our previous example. You can find this code on my homepage. We first import the following libraries and create a 3-dimensional array with the 10 images. Then we create the following vector that tells which digit that is included in the image. Next, we use the following function to convert the integers in vector y into a binary 2-dimensional array. For example, every row in this array will have 10 values, because the network has 10 output nodes. The target probability value of the first output node should be equal to 1, because the first image contains a 0, whereas the other output nodes should have target probability values of 0. Since the second image represents a 1, the second target probability value should be equal to 1, whereas the rest should be equal to 0. By the way, this type of encoding is called one-hot encoding. Next, we could, for example, plot the 4th image in the dataset, which is an image that represents a 3. To get a similar output that I will show later on, you need to set the following seed. Then we build the following network. We will here use just one filter, with the size of 2 rows and 2 columns. Stride is here set to 1, which means that the filter moves only one step down when the filter is moved downwards, and one step to the right when the filter is moved to the right. In this example, we do not use any padding, which means that we set this argument to valid. If you like to add padding, you can change this argument to same, which means that the padding will be added in a way so that the feature map will have the same size as the original image. We here define the size of the images, which is a 5x5 matrix, with only one channel because the image is represented by only one matrix. During the convolution, we use the ReLU activation function and no bias weight. Then we say that we like to use max pooling with a 2x2 window. Next, we flatten the pooled feature map and use a fully connected network with 10 output nodes, where the predicted values are computed by the softmax function so that we get the probabilities from the output nodes. If we run the model.summary function, we will see that 50 weights will be estimated in the fully connected network, and 4 weights for our filter. Then we compile the model, where we define that we like to use an optimizer called Adam, and use the categorical cross-entropy loss function because we have more than 2 categories to predict. Then we say that we like to monitor the accuracy during the training process, which means that we will see the proportion of correct predictions after each epoch during the training. Then we train the network by using 1000 epochs, which takes less than 1 minute on my computer. By setting the batch size to 1 means that only 1 image is used in each iteration to update the weights. If we like, we can plot how the accuracy has changed during the training process. We see that the accuracy is 100% after 1000 epochs, which means that all 10 images are correctly classified by the network. We can now use the trained network to see, for example, how it predicts the first image. The output values gives us the predicted probabilities for each of the 10 digits. We see that the network says that there is a 61.2% probability that the image contains a 0, whereas the probability that the image contains a 1 is almost 0. The probability that the image contains a 5 is about 18%. If we use the argmax function, we can extract the index of the output array that has the largest probability value. Since this index is equal to 0, the network predicts that the image contains a 0. By using the following line of code, we can extract the optimized weights, where these weights are the ones that are used in the filter, and these weights are the ones associated with the input nodes, whereas these are the bias weights. Finally, I will show how to train a CNN based on the classical MNIST dataset, which contains 70,000 images of handwritten digits. 60,000 of these images are dedicated for training and 10,000 for testing. Each image has a height and width of 28 pixels, which means that every image consists of 784 pixels. To train a CNN based on the MNIST dataset, we load the following libraries. Then we set up the training data with 60,000 images and the test data with 10,000 images. Next, we normalize the data so that all pixels have values between 0 and 1. If we like, we can plot, for example, the third image in the training data, which shows a handwritten 4. Then we build the following network, where we use 32 filters in the first convolution and 64 filters in the second convolution. The size of the filters corresponds to a 3x3 matrix. We here also use a hidden layer with 100 nodes in the fully connected network. I here use a batch size of 100, which means that 100 images are used in each iteration to update the weights during the training. This means that 600 iterations are used in each epoch, because we have 60,000 images to train on. Training this network by using 10 epochs takes about 5 minutes on my computer. The network predicts the correct digit in about 99% of the 10,000 images in the test dataset. However, every time you run this code, you will likely get slightly different accuracies due to the random processes during the training. Note that you can get even higher accuracy by tuning on the hyperparameters and by using dropout layers to prevent overfitting. If you like, we can generate a confusion matrix that, for example, shows that 974 out of the 980 images that includes a 0 are correctly classified. 2 images were misclassified as 8s. 1,128 out of the 1,135 images that include a 1 are correctly classified. This is one of the images that were incorrectly predicted by the network. The network thinks that it is a 7, but the true digit is actually a 2. This was the end of this basic video about CNN. Thanks for watching.